Stimulating Neural Plasticity by Cozollino. Part 2. Moderate States of Arousal. I am always doing that which I cannot do, in order that I may learn how to do it. Pablo Picasso. Something we do in all forms of psychotherapy that enhances neuroplasticity is to focus on modulating stress in our clients, regulating subjective units of distress in systematic desensitization, balancing confrontation and empathic attunement in psychoanalysis, or crafting the safe emergency of Gestalt therapy all reflect an appreciation of the delicate balance between challenge and support. We intuitively understand that people need to be motivated and aroused to learn, while simultaneously free from the autonomic activation of a fight-flight response that shuts down cortical plasticity. Knowing how to find and keep clients in learning's sweet spot is a vital element of the art of psychotherapy. The non-technical story goes something like this. When all is well and we are in a state of calm, there is no reason to learn anything new. When our needs for food, companionship, and safety are satisfied, the brain has done its job, and there is little reason to invest energy in learning. At the other extreme, states of high arousal and danger are no time for new cortical learning, but a call for immediate action. A state of mind somewhere between the two appears optimal for new learning and complex problem solving. Anderson, 1976. An attitude best described as interest, enthusiasm, or curiosity stimulates positive arousal. In secure attachment, the child is able to use the parent as a safe haven and avoid experiencing autonomic activation in response to stress. A similar process is likely to take place in a secure therapeutic alliance, allowing CLIs to verbalize their experience rather than defending themselves or fleeing from the situation. The formalization of this notion in experimental psychology, described in a classic paper by Robert Yerkes and John Dodson, 1908, came to be known as the inverted U learning curve. They found that mice learned to avoid a moderate shock faster than one of high or low intensity. They charted their findings on a graph with arousal on the x-axis and learning performance on the y-axis, see Figure 20.1. Over the years, the same phenomenon was found across species in a variety of learning tasks. Broadhurst, 1957. Stinnett, 1957. While this research took place before we knew anything about the neurochemistry of learning, it makes sense that this inverted U pattern will be reflected in the underlying neurobiological processes of learning. Baldi and Bucciarelli, 2005. We now know that learning depends on building new dendritic structures and on the ability of these structures to interconnect. Building dendrites is dependent on the synthesis of proteins guided by genetic transcription, while neuronal firing shapes the architecture of these dendrites to encode new learning. Not surprisingly, the hormones secreted by the HPA axis in response to stress, cortisol, norepinephrine, and endorphins, as well as other learning mechanisms, NMDA receptors, BDNF secretion, etc., modulate learning on the same inverted U-shaped curve. At moderate states of arousal, amygdala activation opens windows of modulated stimulation where top-down plasticity is facilitated. Popescu, Sagian, and Pear, 2007. At moderate levels of arousal, these and many more systems enhance learning, while at high and low levels of arousal, learning is inhibited. Hippocampal neurons require low levels of cortisol for structural maintenance, while higher levels of cortisol inhibit their neuroplastic properties and can even kill them. Gould, Woolley, and McEwen, 1990. Cortisol impacts learning and plasticity by regulating the protein synthesis required for dendritic growth and patterns of neural connectivity, such as LTP, long-term depression, and primed burst potentiation, a low-threshold version of LTP, in the same pattern. High levels of stress also trigger endorphin release, which impedes both protein synthesis and the consolidation of explicit memory, in Troini-Collison and McGaugh, 1987. See Table 20.2 for a sample of findings supporting this pattern of the biochemistry of arousal and its effects on learning. Overall, the various neural systems dedicated to learning and arousal are tightly interwoven. They work together to activate plasticity and learning when it is needed to adapt to challenge, and turn it off in the absence of challenge or when the body needs to be mobilized for immediate survival. The inverted U learning curve reflects both the underlying neurobiological processes and the many overt manifestations of learning seen in the laboratory, classroom, and consulting office. By understanding these principles, we can use them to optimize neural plasticity in the service of positive changes in the brain. Attachment plasticity. Organic matter, especially nervous tissue, seems endowed with a very extraordinary degree of plasticity. William James. Attachment in infancy is usually conceptualized as relationship-specific, while attachment in adulthood is thought of as a general aspect of character. Early attachment patterns may become generalized and self-perpetuating because of their impact on our neurobiology, our ability to regulate our emotions, and the expectations we have of ourselves, others, and the world. The sensory, emotional, and behavioral systems influenced by early attachment experiences can shape our brains in ways that make the past a model for creating the future. We have learned a great deal from attachment research. how our primitive bonding instincts regulate anxiety, how categories of attachment reflect a parent's behavior and a child one's reaction to stress, and how attachment schemas are carried into adulthood, affecting our choice of partners, the nature of our relationships, and the way we parent our own children. Our enthusiasm about the power of attachment categories to explain emotional development often fails to acknowledge the considerable fluctuation of attachment schemas. In our search for a straightforward explanation of intimate human relationships, it is easy to overlook its variability over time and across relationships. In an attempt to support the predictive power of attachment schemas, fluctuation and change are attributed to measurement problems or uncontrolled external variables, such as positive and negative life events or changing relationships. However, we seldom consider that an attachment schema should change because we think of it as hardwired. As we saw in the animal research, maternal attention to rat pups was mediated by the environment in ways that made the pups a better fit to the environment to which the mother was responding. Perhaps because our brains are so much more complex, it takes greater effort and time for us to change, but the role of attachment may be essentially the same in humans. In human subjects, we see that a decrease in security or the maintenance of insecurity during adolescence is more likely to occur in the presence of psychological, familial, or environmental stressors. Adolescents who see their mothers as supportive are more likely to gain security, while maternal depression correlates with a shift from secure to insecure attachment. Overall, secure attachment appears more resistant to change, while negative life events tend to maintain insecure attachment. Hamilton, 2000, Kirkpatrick and Davis, 1994, Thompson, 1982. These findings certainly parallel the animal literature. The major implication for psychotherapy from all of these findings is that insecure attachment is subject to change as a result of positive social input. Poloski et al., 2008. As shown in Table 20.3, the consistency of attachment ratings, primarily secure versus insecure, is 24 to 64%, depending on the study. This may be bad news for those interested in attachment as a stable trait, but good news for those of us in the business of change. As a psychotherapist who is very interested in positive change, the messiness of attachment is welcome. I want attachment schemas to be a malleable form of implicit memory, so relationships with clients can alter them in salubrious ways. This allows psychotherapy to be a guided relationship that regulates of anxiety and fear for the purpose of creating secure attachment schemas. Although there is evidence of organized attachment schemas by our first birthday, they do not appear to be set in neural stone. These naturally occurring changes and the fact that we attach and reattach with many people throughout our lives suggest that the underlying neural systems maintain their plasticity. If you doubt this, ask grandparents whether they feel attached to their grandchildren. In support of the neuroplasticity of attachment networks, research suggests that adults can create secure attachment for their children despite negative experiences in their own childhood. Thus, the powerful shaping experiences of childhood can be modified through personal relationships, psychotherapy, and increased self-awareness. The ability to consciously process stressful and traumatic life events appears to correlate with more secure attachment, flexible affect regulation, and an increased availability of narrative memory. The integration of neural circuitry across cognitive, behavioral, sensory, and emotional domains is the likely neuroanatomical substrate of this earned autonomy. A healing relationship with a secure partner or with a good enough therapist, in which past pain can be processed and resolved, supports neural integration and the attainment of a secure attachment schema. Simpson and Overall, 2014. The power of a healing relationship. Tell me who admires and loves you, and I will tell you who you are. Anton de Saint-Exupéry. Because our brains are social organs and interwoven with the brains of those around us, relationships have the power to heal us. Psychotherapy is successful in large part because of the therapist's empathic abilities and the client's belief in the therapist's humanity and skill. Through the installation of optimism and hope, a therapist, or any healer, uses powerful mechanisms of mind to reshape the brain. The mind's impact on the brain has been studied across a variety of fields from social neuroscience to psychoneuroimmunology and is expressed in such phenomena as expectancy effects and the power of placebos and suggestion. These are all examples of the mind leading the brain via social relationships. The term placebo, Latin for I shall please, reflects the ancient idea that the positive response to an inactive treatment results from the patient's desire to live up to the doctor's expectations. More generally, the placebo effect is the expectation for illness outcome based on what the patient is led to believe by the doctor. Moerman and Jonas, 2002, suggested renaming it the meaning response, reflecting the fact that the placebo effect is mediated via the meaning assigned within the mind of the patient. Until modern times, shamans, in which doctors understood and utilized suggestion of all kinds in their role as tribal healers. Frank, 1963. Similarly, the expectancy effect is likely at play in the fact that ill Chinese Americans born during inauspicious years have significantly shorter lifespans, with the size of the effect related to how strongly they adhere to traditional cultural beliefs. Phillips, Ruth, and Wagner, 1993. Placebo effects are seen as a nuisance in Western scientific medicine, and the patients affected by them are pathologized as weak-minded, impressionable, or malingering. Modern technological medicine has led to a decline in the use of the meaning response, as the role of the doctor has shifted from healer to technician. This is especially ironic given that placebo control groups are a staple of the research upon which their clinical decision-making should be based. Don't the time, money, and effort expended to ensure this standard of research support the very power of patient expectancy to impact symptom expression? Perhaps doctors have become too impressed with technology and have forgotten the power of their humanity. In psychotherapy outcome research, expectancy and placebo effects are relegated to the wastebasket category of nonspecific effects. I would argue that these effects are in fact specific, that is, we know exactly what social and psychological factors lead to healing. Carl Rogers outlined them well during the 1960s as warmth, acceptance, caring, and unconditional positive regard. Epidemiologists call them social support, network connectivity, and spiritual beliefs. Different activation patterns in the brain during successful placebo response reflect the multiple neural pathways involved in mind-brain regulation. In neuroscience terms, the placebo effect is an example of top-down cortical modulation of mood, emotion, and immune activity. Beauregard, 2007. Ochsner et al., 2004. The placebo effect relies heavily upon the prefrontal lobes to integrate social experiences with positive effect and an optimistic state of mind. In the same way that a mother can shape a child's brain by stroking his hair and telling him that things will get better, a doctor can influence a client's immune system by presenting an optimistic prognosis and projecting confidence about the proposed treatment. The placebo effect is a social phenomenon that likely activates the same reward systems, dopamine, serotonin, endorphin, triggered by loving touch and the anticipation of positive connections and feelings. The amygdala, which regulates our experience of fear and pain, is inhibited by positive emotions and activated by negative emotions. Neugebauer et al., 2004. We know, for example, that placebo and opioid analgesia share a common neural pathway, which strongly suggests we are capable of opioid self-administration. There are many examples of the social, top-down regulation of emotion. When a woman holds her husband's hand in the face of threat, fear activation is attenuated. Not surprisingly, the better she feels about the relationship, the greater the soothing effect of his hand will be. Cohn, Schaefer, and Davidson, 2006. Soothing touch is obviously powerful, but so too is a soothing facial expression or a kind word communicated in an attuned emotional state. Some evidence for this has been found when levels of arousal, as measured by skin conductance, were monitored simultaneously in clients and therapists during sessions. During states of matched arousal, there were significantly more positive social and emotional interactions between client and therapist than when they were out of sync. Marcy, Ham, Moran, and or 2007. Even in Parkinson's disease, it is believed that the anticipation of positive reward stimulates the release of dopamine from the nucleus accumbens. Because dopamine depletion is the central cause of Parkinsonian symptoms, this release of dopamine results in symptomatic improvement. See Table 20.4 for an outline of studies that have demonstrated changes in neural activation related to the placebo effect. Table 20.4. The impact of positive expectancy, placebo, on brain activation. Major depression. Increased activity in prefrontal, anterior cingulate, premotor, parietal, posterior insula, and posterior cingulate. Decreased activity in subgenual cingulate, parahippocampus, and thalamus. Pain disorders. Increased activity in lateral and orbital PFC, anterior cingulate, cerebellum, right fusiform gyrus, parahippocampus, and ponsule. Increased activity in the right dorsolateral cortex, anterior cingulate cortex, and midbrain. Increased bilateral orbitofrontal activity and anterior cingulate cortex, contralateral to pain stimulus 5. Reduced activity in anterior cingulate cortex, anterior insula, and thalamus 6. Increased activity in the prefrontal cortex. Activated endogenous opioids in DLPFC, anterior insula, and nucleus accumbens. Parkinson's disease. Reduced activity in subthalamic nuclei. Increase in striatal dopamine. When physicians use the placebo effect to enhance illness outcome, they're using strategies that parallel the core principles of client-centered therapy. For example, an article in the Journal of Family Practice suggested a sustained partnership with patients characterized by an interest in the whole person, knowing the patient over time, caring, sensitivity, empathy, being viewed as reliable and trustworthy, adapting medical goals to the needs of the patients, and encouraging their full participation. Brody, 2000. Another physician in a piece from the British Medical Journal asked, for 1,000 years the action of the placebo has made vast numbers of patients feel better. Have we today provided a consultation in which the placebo does not act? Thomas, 1987, page 1202. These are the aspects of traditional healing still employed by psychotherapy that appear to have been lost in the morass of modern technological medicine. The implications of the power of the placebo effect to change the brain are profound. Yet our awe of science leads us to underestimate the importance of the doctor's role as healer and patients' abilities to contribute to their own healing through the modulation of their endogenous biochemistry. There are many ways in which the power of the placebo effect could be harnessed and used to increase the effectiveness of medical treatment, including increasing visits, encouraging and supportive interactions, and shaping patients' experiences by telling them what positive outcomes they should expect. Wallach and Jonas, 2004. See Table 20.5 for a list of their suggestions. Ironically, we are only required to tell clients of the many risks and potential negative side effects of treatment, which likely create negative expectancies and self-fulfilling prophecies. Table 20.5. Leveraging the placebo effect in medical treatment. Increase frequency of contact. Determine what treatments your patient believes in. Align beliefs between patient, doctor, family, and culture. Be sure you believe in the treatment you are administering. Inform patients about what they can expect. Deliver treatment in a warm and caring way. Listen and provide empathy and understanding. Touch the patient. Findings from a medical research supporting the power of specific doctor-patient interactions. Adapted from Wallach and Jonas, 2004. All of the givens of classical healing and psychotherapy have been squeezed out of modern Western medicine. Perhaps these non-specific ingredients of a healing relationship will someday be woven back into medical practice. Summary. The power of psychotherapy to change the brain rests in our ability to recognize and alter unintegrated or dysregulated neural networks. As knowledge of neuroplasticity and neurogenesis increases, so will our ability to impact and alter the brain. The possibility exists that sensitive periods can be reinstated in the context of psychotherapy, and that stress can be utilized in a controlled manner to edit and re-edit emotional memories. Post et al., 1998. Although the practical application of these principles to humans remains on the horizon, the ability of psychotherapy to sculpt the brain is evident. It is certain that psychotherapists are already enhancing plasticity without the help of genetic manipulation or chemical interventions. Therapy is a safe emergency because of the supportive structure in which difficult emotional learning takes place. A client's sense of safety is enhanced by the therapist's skill, knowledge, and confidence, which support emotional regulation and maintaining moderate states of arousal. It is quite possible that the caring, encouragement, and enthusiasm of the therapist also reinforce learning, neural growth, and plasticity through the enhanced production of dopamine, serotonin, and other neurochemicals. Baird, 2000. Kilgard and Merzenich, 1998. Kirkwood, Rosas, Kirkwood, Perez, and Baer, 1999. Successful therapeutic techniques may be successful because of their variability to change brain chemistry in a manner that enhances neuroplasticity. In the recent shift to neural optimism, critical periods of neural development are no longer seen as the final word on neural structure. The impact of enriched environments has demonstrated the brain-building capacity of positive experiences throughout the lifespan. More recent research in neural plasticity, e.g., use-dependent plasticity, neurotransmitter alteration, stem cell implantation, suggests that new experiences and future potential biological interventions may be capable of providing us with many tools with which to rebuild the brain. Psychotherapy is on the verge of an exploding new paradigm. The psychotherapist as neuroscientist.